Solutions provide a medium for reactions between ionic compounds to occur. Now, if you took a solid crystal of sodium chloride and mixed it with crystals of silver nitrate, these two react, but the reaction would go very, very slowly. What has to happen is for the silver ion in here, the silver 1 ion, you could say, it's got to attach to the chloride ion over here, and the sodium ion will attach to the nitrate ion over here. And because they're locked in crystals, they can't get at each other, and the reaction doesn't occur. All that changes when you put them into water. When you put them into water, you can write an AQ after the formula, and that means aqueous. That means dissolved in water. And what you really got in that case are ions with those icy shells around them that we talked about in a previous lab. You've got a sodium ion in there and a chloride ion in there. In here, can you break this one up? The nitrate ion is on your polyatomic ion list, and you would have to know that that is a -1 charge. So you have to know this to be able to break it up correctly. And then that will make the silver have a +1 charge. Silver is a transition metal, so it is not so easy to see from the periodic table that it's got a +1 charge from where it is. You have to assign the charge to the nitrate first before you can work out what it is for the silver. And we've done some of this in previous worksheets. Now what actually happens in solution is that these ions all can separate. They all get their icy shells around them, and they separate, and now they can swap partners. The positive ion here can go after the negative ion there, and the positive ion here can go after the negative ion here. So what you're going to get is sodium combining with NO3, and you're going to get this when you put those ions together. And when you put the silver together with the chloride, you get this. So you happen to get this. Now, if I go and look up how soluble are these in water, does this dissolve in water? It does. If I look up something called the solubility in a table or online, and it's greater than about 1/10 of a gram per 100 milliliter of water. In other words, if you can take a pinch of this that's about 1/10 of a gram and dissolve it in 100 milliliter of water, or take more than that and dissolve it in water, you can safely put an AQ after this to show that that product is going to be dissolved. Now, if you go and look up the silver chloride, it has a solubility that's less than that. So for that, if it's less than that, I will write a solid after that because it will not dissolve in water. So this is my reaction. Now, is it balanced? Well, let's see. I've got a sodium here and a sodium here. I have a chlorine here and a chlorine there. I have a silver here and a silver there. I have an N here and an N there. I have 3 oxygens here and 3 oxygens there, so it's balanced. Now this lets you write reactions between ionic, this procedure lets you write reactions between ionic compounds in solution. Let's break it down a little bit, the steps that we did, and look at it like a step-by-step procedure so that we can apply this, what we just did, to other reactions. And your number 4 in your worksheet is like this, and so are some of the ones on the end of the worksheet. The first thing I'm going to do is write the formulas of the reactants. So I had to write down the formula of the sodium chloride and the silver nitrate down. They might give me, if it's mean, like question number 4 is on your worksheet, they might just give me the names of those compounds, and then I have to write down the formulas. So you can see that this builds on to what we've done earlier. Once I do that, I list the ions present. So what ions are present in each of these ionic compounds? I have to break them up and just list the ions that are there. Now I don't have to say how many of each type of ion I've got. Just list the kinds of ions that are present. Alright, so we saw that these were the 4 ions that are present, and the next step is swap the ions to write the products. So I took, and you can always do this, you can take the positive ion in one of them and put it with the negative ion in the other one. Now the positive ion here is not going to go for the silver because they're both positively charged. It's going to go for something that's oppositely charged. And that'll keep that straight. Now I've got to put the ions together so that their charges balance. This was a +1 and this was a -1, so that was easy. And the same thing here, +1 and a -1. So that was fairly easy in this example. The fourth thing I want to do is check to see if the products are soluble. That is, I can put an AQ after them, or insoluble. And I can put an S after them. Now, you can go look up the solubilities for these things. Like if you say solubility NaNO3, it will give you a number. It'll tell you how many grams of that will dissolve in 100 milliliters of water. And you can decide whether to put an AQ after it or an S after it on that basis. Now, in the textbook, there are some guidelines, some rules of thumb that work sometimes, most of the time, that will let you predict whether something is soluble or not just by looking at the formula. For example, there's a rule in the textbook, and it says if you've got an alkali metal in your ionic compound, it's going to be soluble in water. So we have a sodium there, and you can put an AQ after it. There's another rule in the textbook that says if you've got chloride, bromide, or iodide in your compound, that will be soluble unless you combine it with silver, mercury, or lead. So some of these rules have some exceptions. This one is an exception to the rule, and it's not soluble. If you go and look up the solubility for that, you're going to see that it's not soluble. So you're going to have to either look up the solubility, or you're going to have to use one of those rules of thumb, which I don't expect you to memorize. You do not have to remember the solubility rules from the book. I'm going to assume that you're going to just go look up the solubilities for things to decide if you put an AQ or an S after it. The fifth thing we did is balance the equation. So this is a 5-step procedure for writing what we call a molecular equation. So this is the procedure for doing that. Now let's apply it to another reaction. See if we can do it. How about one that is kind of similar to your number 4 in your worksheet? Suppose I have ammonium sulfide reacting with nitric acid. And I want to write a balanced molecular equation for that. All right, let's go through this step-by-step procedure. Step 1, write the formulas of the reactants. Well, now I already know how to do this. Take the name of something and write it as a formula, right? Because we spent a whole worksheet on that. How did I write that down so quick? Well, to write that down, what I had to know were the charges on the ions. Remember how we did that? I would have to know sulfide is S-2. And I could look that up on the periodic table. It's in the column where you get -2 charges. Now, if I've got an ammonium ion, that's in my polyatomic ion list. So I would have to put 2 of these together with 1 of those to get a neutral compound, and that's how I got the formula for that. Nitric acid. Okay, it's got an ic acid ending, so I know it has an ion inside that has an ATE ending. So it must contain the nitrate ion. Because 8 is the name of the ion that's inside of something that ends with ic acid. Alright, and it doesn't have a hydro in front. So I have to remember what the formula for the nitrate ion was. That's got a -1 on it. So if I want to do the acid, I have to combine that with a hydrogen ion. And when I put those together, I'm going to get HNO3 as the formula for nitric acid. Okay, so I have my 2 reactants, this and this. All right, let's do step 2, list the ions present. Well, writing the formulas down for the 2 reactants gave me the list of ions, so there's not too much for me to do with step 2 here. The ions that are present are NH4 plus and S-2, and over here in this one, there's H plus and NO3 minus. And these are my 2 reactants. Okay, now I'm going to swap the ions to write the product formulas. Okay, the positive ion here is going to go after the negative ion here. Now that's got a +1 and this has got a -1. So I'm going to get NH4 NO3. They go together 1 to 1 like that. Now what about the formula here? The positive ion here is going to go after the negative ion there. What's my other product going to be? Is it going to be HS? No, because this is a -2, so I need 2 of these. So it's going to have to be H2S. All right. So here are my 2 products. Now I can write the equation down. Let's check and see if these are soluble or not. If I go and look this one up, or if I look up the guidelines in the book say anything with a nitrate in it is soluble. And they say anything with an ammonium in it is soluble. So both ways, this will be soluble. So I know my reaction is going to look something like this. Anything with an ammonium in it is soluble, so I can put an AQ after that. And this is my reactant. Here's my other one. All acids are soluble, or they wouldn't be acids. They have to release hydrogen ions in solution, or they're not acids. So you can always put an AQ after something that you recognize as an acid. Remember how you recognize acids? If it starts with an H, it can act like an acid. All right, and then here's my products. If I go and look up H2S, it says that that's not soluble, terribly soluble in water. And if I look up the solubility from it, and it says also that it's a gas. So instead of being a solid, instead of it dropping out of solution, it will make bubbles of this foul-smelling gas. It smells like rotten eggs. And then we have our other product, ammonium nitrate, which we've already said is soluble. So far my equation looks like this. The last thing I need to do is balance this equation. Now if I look at it carefully, it's not balanced. If I put a 1 in front of this, there are 2 ammonium ions there. And that means I need 2 ammonium ions on this side. So I can sneak a 2 in front of that. So you don't have to balance by atom, you can balance by ion too. Because there are ammonium ions on both sides, those have to balance as well. Now when I put a 2 here, that means that there has to be 2 nitrates on this side. So I must have to put a 2 there. And that'll give me 2 nitrates. Now, how about everything else? I've got a sulfur and a sulfur. And how many hydrogens? 2 hydrogens on this side that are outside of the ammonium, and 2 hydrogens on this side that are outside of the ammonium. So this is balanced. Verify it yourself. How many nitrogens on this side? Well, there's 1, 2 there, 2 nitrogens there, and then there's 2 more here. So there are a total of 4 nitrogens on this side. So look at this. There's 2 nitrogens there and 2 more there. So there are 4 nitrogens on this side. When you put a 2 in front, it multiplies everything that's in the formula by 2. Try that with all the other atoms, the oxygens, and verify that it's balanced. That is how you write a balanced equation for a reaction in solution that involves ionic compounds. You don't have to have the products given. You can work that out yourself. And there are several like that on the worksheet.